Okay, now we want to look at chi-square test of independence, two-way table. So now we are trying to um, examine whether two variables are related. Okay, so they have an example, but I want to start with maybe something not quite so um, big as far as numbers, that kind of thing. So maybe we'll go back to basketball or something like that. Again, this is section 3.4, chi-square test of independence. And I think you want to talk about the name here, test of independence. Whoops. And so what's happening is I have two variables. Okay, two variables. Each is categorical. And so if I set up these two variables, say I have an explanatory and a response variable. So here I'll say this is explanatory, this is response. And we've got category 1, category 2, category 3, say. And on the response, maybe we have row 1, and we'll just stick with 2 rows. And the reason I'm going with 3 columns, I could go with 2 columns, and this would be very similar to our difference of 2 proportions. And it's just an extension of that. But this way, I think we can see a little better maybe what's going on. So because these are categorical, I would have count data for each of these. And so it really doesn't matter, we'll talk about maybe what these explanatory and response variables could be. But let's just think very generally here about the structure and what we're looking for. And so suppose I counted, and there were 10 times that I had this row 1, whatever that category was, with column 1, and maybe 20 times there, and we'll go with 30 times here for a total of 60. And suppose I row 2, it was 100, 200, and 300, something like that. So I just, I only had 60 times that I used, that I had the response variable R1, or with the category R1, and maybe 600 times with the category R2. Yeah, sure, could have happened. And similarly, 110, 220, and 330 here. But the point is, when we look at this, we're looking for either independence or dependence between our explanatory and response variables. And the way we judge that is, remember that two variables, okay, in an intuitive sense, two variables are dependent if knowing something, the right thing, I guess, knowing something about one gives me new information about the other. Okay, I mean that's intuitively what our dependence means, and then two variables are independent. So two variables are independent if that's not the case. So independent if knowing something about one, oh, I didn't have one in here, about one gives no new information about the other. And so as we look at these tables, we look up here, and so let's pick a row. So suppose I'm in here. What that row, I can see about the explanatory variable here, or better yet, since we're talking explanatory variable and response variable, let's say usually you want to predict things from the explanatory variable, and that's why we call it explanatory. So suppose I'm in column 1. What that tells me is it's close to 90%. It's not exactly. I probably should have made the top row 10 and the bottom row 90 and so forth to make it exactly 10% and 90%, but they're close. And so as I look at column 1, what I would say is, if I know I'm in column 1, I would guess that row 1 takes up about 10% of the cases and row 2 takes up about 90% of the cases. Okay, right? You see where that's coming from? They're 10, and I could go ahead and change these just to make it much more clear with the 90s, so you don't get too worried about my estimated percentages. So I could make that 180 and 270, in which case this would be 540 total. This would be 100. This would be 200. This would be 300, and overall we have 600. Okay, so 10% are in row 1, 90% in row 2. Okay, that's what it tells me in column 1. Now if I go to column 2, it doesn't give me any different information. In other words, I haven't gained something new about going into column 2, because it's still 10% and 90%. So if I was trying to make a prediction of some kind, I wouldn't make any different prediction if I knew I was in column 1 or column 2, right? I'd make the same basic prediction. I would guess that 90% of the time I would find myself in row 2, and 10% of the time I would find myself in row 1. Nothing different. And then similarly, if I go to column 3, no new information, 10%, 90%. Okay, 10% for the top, 90% for the bottom. Everything's the same, independent. Okay, I got no new information about the row given what column I was in. So I learned something, so somebody tells me, oh, you're in column 2 on the explanatory variable. Great! Does that help me in any way with the rows? No. I have the same basic prediction every single time. So this is a perfect sort of independence. When these rows look exactly the same in terms of relative frequency, okay, so if if I'm thinking of a percentage, a proportion of the total, right? So 10, 20, 30 are proportions of 60, 90, 180, 270 are proportions of 540, or going the other way, 10 and 90 are proportions of 100, 20 and 180 are proportions of 200, 30 and 270 are proportions of 300. So, you know, I might have a P11 there, row 1, column 1, P12, P21 is what I meant. I'm sure that's what I said. P21, P12, P22. These, you know, if I looked at these as proportions, P13 and P23, then independence, okay, perfect independence, independence says P11 equals P21, P12 equals P22, and the proportion represented by P13 is equal to the proportion represented by P23. Okay, and so we could look at it that way. Now, those are proportions. If I'm doing these equalities this way, those are proportions based on the rows. Okay, those are proportions based on the rows. And similarly, if instead I made proportions based on the columns, I would say something similar. So these are based on the rows. So in other words, what I did was, if I had actual numbers in here, like an N11 and an N12 and an N13, and then just an N1 for row 1, you know, I had something like P11 was N11 over N1. Okay, so these are by row that I said that up there. Okay, and similarly, you know, I'd have an N2 and a N21, N22, N23. Okay, those are the numbers like these numbers up here. So I had 10 out of 60, 20 out of 60, 30 out of 60. So I had 1/6, 2/6, and 3/6 going across. Similarly, going across, I had 90 over 540, 180 over 540, and 270. And again, that was 1/6, 2/6, and 3/6. So those were exactly the same going that way. Okay, so I can do it by row. That would be one way to look at it, and that's fine. Okay, by row. I can also do it by column. And in this case, if I'm looking by column, then I'll use an uppercase N1 and an uppercase N2 and an uppercase N3, in which case then if I created some of these, now I'm going to name them, instead of P's for proportion, I'm going to use Q, just to make sure you realize I would be looking at different proportions as I'm doing this. So here I would have my Q11, Q21, Q12, Q22, Q13, and Q23. And in this case, my Q11 is equal to the N11, but over uppercase N1. And so if I'm doing it by column, then, you know, whereas here, these proportions are the same, I would look across the rows and I would say, oh, the Q11 proportion is equal to the Q12 proportion, which is equal to the Q13 proportion. okay, because I'm dividing this way. And similarly, you know, Q21 is equal to Q22 is equal to Q23. And that would be independence. Okay, because you see what this is saying is, if I do it by column, I'm saying that it doesn't matter what column I'm in, this proportion in here relative, you know, for the row in this column, it's always going to be the same. Nothing changes. Doesn't help. So let's look at back at our basketball example that we had done. So for our basketball example, again, you know, we looked at two variables. Now in this case it was 2 by 2 to start with, right? We had before and after. Okay, so the one variable was our practice, and the other variable was just the outcome. So did practice somehow predict something about the outcome? And that was success and failures. Now, if let's say, okay, again we had you know, maybe 50 each time, and suppose you know, before we had say, you know, 35 successes and 15 failures, and then after practice, after practicing and so forth, we tried it again and we had 35 successes and 15 failures, right? Then hopefully, and here's 70 and here's 30, hopefully what you would say is, oh, practice didn't matter, okay? In other words, our outcome, our free throw shooting, was independent of our practice, because practice didn't help. You know, if you told me, if you tell me, hey, okay, before practice, what would you guess? Well, if I kind of know the data, I would say, well, oh, before they practice, I would guess that they're going to make 70% of their free throws. Right, 35 over 50. So by column, I'm going to look at 35 over 50, 70%. That number right there out of our 100. And then you say, oh, okay, but wait a minute. Now they've had practice. What are you going to predict? I'm still going to predict 70%, 35 over 50. Okay, so knowing they had practice or didn't have practice didn't help me a bit. I ended up needing to predict the same thing. Okay, so that is independence. Now, you know, and that's perfect independence. And if I had a table like that, I don't need no stinking hypothesis test. I can just tell you, yep, they're independent. Null hypothesis will not be rejected, will fail to reject the null hypothesis, because the null hypothesis is that everything's independent. Okay, so now though, you know, if we have that same scenario, here's before, here's after, here's successes, here's failures. You know, if that was 30 and 20 out of 50, and then it was 45 and 5 out of 50. So this is 75 and 25 and 100 total. So here though, Now, all of a sudden, if you tell me, okay, a bunch, they're coming in, they haven't had any kind of practice, they don't know anything about style and setting up right and all that kind of stuff. What are you going to guess? Well, I'm going to guess probably about 60% success, right? 30 out of 50. So I'm going to use those and say I'm predicting 60% success. But now you tell me, oh wait, no, I'm sorry. No, they have had practice. So if they're in the after column, what are you going to guess? Oh, I'm going to guess they're going to be about 90% successful. Okay, 45 out of 50. I'm going to guess they're around 90% successful. And so this one looks like dependence because I changed my guess. Okay, and this one looks pretty obviously, we can try this in our template, this one looks pretty obviously to be a dependent situation, that we would reject the null hypothesis. However, that's the thing, you don't know. So, starting back here with the 35 and 35, well, imagine, right, instead of 35 and 35, you have, say, 34 here, 36 there, and 16 and 14. Oh, well, yes, they're different, but they're not a lot different. Could that difference, remember we're doing random sampling, could those differences actually be just from chance? In other words, the populations we're pulling from, are they actually independent? And that we just happen to have a difference because of random sampling? That's the big question that we're trying to answer. Because almost always, due to random sampling, you're going to get something a little different. And let's look at a very specific case where it would have to be different, right? So suppose for whatever reason, okay, here's before, here's after, they took 53 throws, but for whatever reason in the after, maybe I had 50 people doing it. I don't know. And maybe one of them was sick, so I only had 49. And let's just go with, this was 25, that was 25. Well, I cannot possibly match the first column exactly, right? If this is successes and failures, I could have 25 and I could have 24. Well, when you think about it, if these are truly independent and so forth in a perfect situation, I would expect either the 25 on top, 24 on bottom, or 24 on top, 25 on bottom, but these numbers are not exactly the same. Okay, so due to random sampling and other things, I didn't get the same percentages. I did not, this proportion compared to that number is 50%. This one is more than 50%. Not a lot more, but it's more than 50%. They are not the same. So, to see something like this and to say, oh, well, yeah, they're different, so maybe there's a dependency. Well, maybe, but I kind of doubt it. I doubt statistically we would show that we're pretty sure these must have come from two different populations. I look at this and I think, yeah, I think these two things came from different populations. 60% effective, 90% effective, right? 60, 90. That looks very different to me. Here, not so different. 68%, 72%. Not so different, especially with only, 50 in each column. So, I don't know. I doubt this one would come up as dependent. All right, so that's what we're trying to do. And it works much like the chi-square goodness of fit. We have to come up with an expected value and so forth. But let's just, for now, this video is getting pretty long. Let's just check a few of these. So here, let's check this in our template and see what our p-value is. So let me go here. So there's our template. I'm going to get rid of all that. Whoops. I'm going to try to get rid of all that. And so we had 30 and 20 and 45 and 5. Now notice what happens here in our expected counts. So I'll just point out that what happened was, so what we're testing against is we're kind of pooling these numbers, the 75, 25 and the 50 and 50 down here. And we're saying, well, what kind of table would be perfectly independent for those summary numbers at the ends? And so see, these summaries are 75, 25, just like the ones up there. The ones down here are 50, 50, just like these. So here would be, for those column numbers, or margin numbers as we would call them, 37 and a half, 12 and a half, and then 37 and a half, 12 and a half would be a perfectly independent situation. And so what this is going to do again is simply check the difference between this expected perfectly independent set of numbers and the numbers we had up here. So it's just going to do those subtractions. It's going to square them, divide by the expected number. We get these numbers, it adds them up, and there's our p-value of 0.0005. So very small p-value. And so in this case, if we come back here, we had a p-value equal 0.0005, I think. So very much smaller than 0.05, and so we would reject H0, meaning that we think, at least one of these proportions, relative proportions in here, is different. And so we're saying variable 1, or the response, response and explanatory are dependent. Okay, it matters. I can get some information by knowing something about the explanatory variable, or for that matter, the response variable. So I can really do the prediction either way, right? I could predict knowing the response variable. If you say we're in the success row, I would say, well, probably, right, the after practicing is going to have more successes. Yes, and it does, 45 to 30. Okay, so that is this idea of the chi-square test of independence. We're looking at two categorical variables, looking at their counts, and we're asking, hey, do those counts make a table that if we reduced everything to sort of proportions, either by column or by row, so we could do it by row and look at these proportions, and we should find that the proportions, if we're doing it by row, as we look at up and down each row, we should have the same proportion for that column every single time. Okay, so that was taking our raw number and dividing by that total. Okay, so we could do it by row, and those we should be able to look up and down and see the same type of proportions, or we could do it by column. It doesn't matter. In which case column, then I would look at my raw number up here divided by its column total, and as I look across those columns, I should get always the same proportion across there. Okay, that would be perfect independence. If they're reasonably close, then yeah, they may, it may just be due to, the only reason they're different is due to random sampling, and that's what we're trying to figure out. Is the difference, like when I look at that, is that difference due to random sampling, or is there probably really a difference between the before practice and after practice? Okay, and in this case up here, yeah, it looked like there is a difference, and we got a p-value that was very small that supported that difference. In this case down here, probably not a difference. And so real quick, I'll change those numbers in the template back here to be, whoops, not those numbers, to be 34, 16, 35, no, 36, and 14. And when I change those, I get this huge p-value of 0.66. I have a 66% chance of generating numbers like this if by random, if the null hypothesis is true, which is that all the rows or all the columns have those same relative frequencies. Okay, so in this case, for this one, I would get a p-value of 0.66, and we fail to reject H0, in which case, now typically we frame our, there's not enough evidence here to say they're independent, to say they're dependent. Not enough evidence to say dependent. Now, in this case, with the numbers being so close, I probably would just go ahead and say, oh yeah, they're independent. Okay, but that is this idea of the name chi-square, way back here, test of independence. That is what we're doing with this test. So we'll stop that because that's plenty long.